welcome to the third lecture in the Language Models and Intelligent Agentic Systems course. Today we're going to be covering neural scaling laws. So I alluded this to a couple of times in the first lecture, and today we're going to cover it in a lot more detail. I want to begin with this quote, which I think is really interesting, which is from Dario, who is the CEO of Anthropic and used to be at OpenAI. And it was just before OpenAI started that I met Ilya Sutskever. One of the first things he said to me was, look, the models, they just want to learn. You have to understand this. The models, they just want to learn. All right, so last lecture, we went through the transformer architecture. So I walked you all the way from what happens when you give a string of words as input to how do you get probabilities over the next token in that sequence. So you tokenize, you map to token IDs, you map to input embeddings. From there, you add positional encodings to encode information about the order in which the words come. You feed this into the transformer architecture, and we covered that in quite a lot of depth about the different components within that architecture. And then you get output embeddings. You map these to logits. You map these to next token probabilities, and that's the output of the architecture. Right? So this is what we did last week, or on Wednesday rather. And I'm also going to allude back and remind you of some of the stuff we covered in the first lecture. So in the first lecture, I covered how these systems are trained. They're usually trained using a generative pre-training method, which basically means you do unsupervised next token prediction over a large corpus of data. So you have a massive data set of text, and within that text, you get the model to predict the next word that happens in the text across that entire corpus. And this is called next token prediction. And I argued that next token prediction is a very hard task if you're going to perform it very well, and that performing it well requires understanding the rules of text. I also argued that there's a way of looking at next token prediction over a very large corpus of text as essentially training on a very large battery of tasks. So you have within the text many different tasks that the model has to get good at, and then the model has to naturally learn solutions and internal cognitive methods that generalize across all of these tasks. And today, the reason I'm bringing this up now is that we're going to return to this viewpoint, and I'm going to give you a little more evidence that this is a good or accurate way to think about what happens when we do generative pre-training. Okay, so what are we going to cover today? So today can roughly be broken up into the following parts. First of all, I'm going to argue that as we go on forward in time, more and more compute will be expended on these models. This is not going to take very long, but it's good for you to see the data for yourselves. And then I'm going to argue that more compute equals lower loss, that if you throw more compute at these models, they will achieve a lower loss. And then finally, I'm going to make an argument that as this loss gets lower, these models will exhibit more intelligent behavior and more latent capabilities. And by latent capability, I mean something the model can do that we can then access in some way, that we can then bring out from the model. And next lecture, we're going to talk a whole lot more about bringing these latent capabilities out of these unsupervised learning models. So today, we're still in the realm of unsupervised generative pre-training. So we're just sort of wrapping up all those threads from Monday and Wednesday. All right, let's get started. So the first topic to cover is more time equals more compute. So this is a graph taken from Epoch AI. Epoch AI is a very well-respected forecasting company about AI trends. So they try to look in a data-driven way about how AI as a field has evolved over time. And this is one of their most famous works, where they look at notable AI models through time, and they track how much compute was used to train that model, right? And what you see is that there's some noise here, but over time there's a clear trend of increasing the amount of compute that's spent on models. One notable thing to take into account when looking at this plot is that the y-axis here is logarithmic, right? It's not a linear axis, it's a logarithmic axis, which means that moving up the y-axis by a fixed amount corresponds to multiplying the compute by a fixed amount. So yeah, the training compute here is measured in flops, and we can see that models that were trained back in 1956 used, the largest ones used around 10 to the 6 flops, And then if we look at, say, 1986, we're then looking at 10 to the 10 flops, which is 10 to the 4 more flops, right? So it's several orders of magnitude more flops. And the pattern that they look at in this range of time from 1915 to 2010, the amount of compute that's thrown at these models grows by roughly a rate of 1.5 times each year. So every year, the frontier model, the models that are largest, the ones that we've thrown the most compute at, increase that amount of compute we throw at them by a factor of 1.5. Right? But then in 2010, we enter what they dub, so historically, this compute has increased by a factor of 1.5 times per year. And then in 2010, we enter what they call the deep learning era, where the amount of compute we throw at models as a function of time increases significantly to 4.6x per year. And in this deep learning era, what marks this out is that we find a very effective way of leveraging compute, right? And that's for learning, right? We find algorithms and methods for using and leveraging compute to learn functions, and that's what enters into the deep learning era. And at this point, it becomes even more effective to throw compute at models, right? The bang for your buck that you get from increasing the amount of compute investment goes up significantly in this era. And so the amount of compute we throw at models goes up by roughly almost 5 times each year. And you can see that this point is dominated by a lot of language models. So the sort of teal-colored ones that are all stacked towards the end, these are language models. So the largest models that we're training nowadays tend to be language models, as opposed to previously, we had a lot of things in robotics and vision and all of that stuff. All right? Any questions about this? Yeah? So it's a very simple historical trend that as time goes on, the amount of compute we throw at models increases, and it's increasing at this, this geometric fashion. We're multiplying the amount of compute by 5x each year. All right, great. To get like an idea of this, to really see this, I want to plot for you the sizes of GPT-1 through 4, right? So here we have this tiny little speck here. This is GPT-1. The number of parameters it has is 117 million, which sounds like a lot, but is actually tiny. It's a tiny, tiny model. At the time, it was reasonably large, and that time was in 2018. Next, we have GPT-2. So this has 1.5 billion parameters. And as you can see, it's significantly larger. It's roughly 10 times as large as GPT-1, a little over that. And then finally, in 2020, we trained GPT-3, which looks like this, right? Gigantic compared to GPT-1. So this is a point where we really start throwing a lot of compute into these models. Okay, so that's 1, that's 2, that's 3. I'm not even sure if you can see 1 from that far away. This is what 4 looks like compared to that. This has 1.76 trillion parameters as an estimate. We don't know the exact number. I don't think it's been confirmed, right? So really, it's a massive increase in the scale of these systems over time. All right, great. Any questions at this point? All right. Wonderful. So next we'll move on to the more interesting part of today's lecture, which is that more compute gives you a lower loss, and it does so very reliably and robustly. Right, so let's take a look at this. So we're going to spend some time looking at this paper from 2020 called Scaling Laws for Neural Language Models. This paper introduces the notion of a neural scaling law. So what is this? A neural scaling law is an attempt to derive a mathematical relationship between various variables that exist when you're training a model. So first of all, the loss. So what loss is my model going to achieve once I've done training it? And this is test loss, not train loss, right? So it's the loss that the model achieves on held out data rather than data that it's seen, okay? The next is the number of parameters in the model, n, right? It turns out you get much better fits if you use the non-vocabulary parameters. So you're ignoring those embedding and unembedding matrices, which map you from the vocabulary space into your latent space. You ignore those embedding and unembedding matrices. You're only interested in the non-vocabulary parameters, so all the stuff in the body of that transformer. The next is D, which is the size of the data set used to train the model. So how much data are we going to throw at the model? And finally, C, which is the total compute used to train the model, right? So fundamentally, at base, we're really interested in the relationship between L and C, right? As I throw more compute at the model, what's the loss going to do, right? So let's begin by thinking about, suppose that I have, say, an infinite amount of data and an infinite amount of compute, but a finite model size, right? In that case, I am bottlenecked by the model size. There's a limit to how well I can do with a model of this size, even if I had as much compute as I like and as much data as I like, right? So in that case, we say we're bottlenecked by model size. And so in general, I'm going to hold one of these things constant. I'm going to hold one of these things constant and be bottlenecked by it and have an infinite quantity of the other two things. And then I'm going to ask, what loss do I achieve given that I'm bottlenecked by this particular thing? Okay. So this is the question that we're going to try to answer. We're going to try to derive a mathematical relationship between the loss I end up at and the bottlenecking variable. Okay, so the first bottleneck we'll consider is the number of parameters. So this is exactly the situation I just described. I have an infinite amount of data, an infinite amount of compute, but only a finite number of parameters. How good can I do? So what's our methodology? Well, we're going to fix the number of parameters. We're going to have a range of models that vary in size, fix the number of parameters in each of those models. And then we're going to train those models until convergence on the until they've reached a point where the test loss stops going down. And so the data set size, the compute won't be bottlenecks. We'll throw as much compute as is needed and as much data as is needed to get that loss to convergence. And we're going to plot the test loss as a function of the number of parameters. And what we end up with is this mathematical relationship. So let's see that on a graph. So this is what we're looking at here. So on the x-axis, this is parameters. It's non-embedding, so again, not the vocabulary parameters, the parameters in the bulk of the model. And on the y-axis, we have the test loss. Again, this graph is a log-log plot, which means both the x-axis and the y-axis are logarithmic. And if you take a log of both sides of this equation, you get a straight line on a graph. And that's exactly what we get here, a shockingly good straight line on a graph. Like, the level of precision of this line is crazy to me. It's really, really exact. The exact values of the parameters nc and alpha n are found in that plot. They're not actually particularly interesting. The interesting thing is the fact that you can plot this at all. So we see that when we're bottlenecked by the number of parameters, I end up with this, this relationship here. It's a power law relationship between the loss and the number of parameters in my model. Let's briefly talk about just a digression around model shape. So here are different shapes or different ways that you could change the shape of your model, right? So in general, specifying the number of parameters in my model doesn't tell me the exact model architecture. So for example, I have a model that looks like this. I want to double the number of parameters. I could either double the number of layers, so stack it twice as high, or I could double the width and stack it and make it twice as wide. That's just a simplistic one for an MLP. But the general principle is you can mess around with things like depth and width and get the same number of parameters for different shaped models with different architectures. And what this is kind of arguing is that the model shape doesn't matter nearly as much as the number of parameters in the model. So here they have different ways that you can vary the sizes of the things within the transformer architecture. So the ratios, they have various ratios plotted here of one size to another size. And they're sweeping across them again logarithmically. They're looking at what happens to the loss, or rather how much of the loss you increase as compared to the sort of optimal size. And they argue that, provided you do something sensible, so provided you're in a kind of sensible range, it really doesn't matter that much. You get some loss increase, but it's pretty trivial, right? So, this scale goes up to 10%, which is really like not a whole lot, right? So again, this is another one here where you can vary across this like several orders of magnitude, and you really only go up a couple of percentage in loss. So this is another lesson that comes out of this paper, is that really the model size is the thing that's driving this, and the model shape is like comparatively less important. You do get some gains. There is like an optimal shape. There's an optimal way to set these. But really, as long as you're doing something sensible and you're not like scaling your model by just making it really, really, really deep or really, really, really wide, you do something sensible when you scale your model up, you'll basically be fine. Right? So let's consider another bottleneck, which this time will be dataset size. So instead of bottlenecking by number of parameters, I'm going to bottleneck by the amount of data I have available to me. So I'm going to fix the number of training examples, fix the size of the data set, how much data I've got available. I'm going to train a very large model. So I'm going to assume I'm not bottlenecked by number of parameters by training a very, very large model. I'm going to train it until the test loss stops decreasing. Right? So again, compute isn't going to be a bottleneck. I'm going to have a very large model, so I can, and I'm going to train it with as much compute as is necessary until my test loss stops decreasing, but I only have a certain amount of training examples that I can use. I can reuse these as many as I like, but eventually I'll start overfitting, and at that point my test loss will go up again, and that's the point where I sever the training. So I'm not bottlenecked by compute, I'm not bottlenecked by the number of parameters, and I'm going to plot the test loss as a function of the number of training examples. And the punchline is exactly the same. The loss, test loss, is a power law relationship of the number of examples I have in my dataset D, and it has exactly the same form. And again, if I plot it on a log-log plot, I get a straight line, a really precise straight line through these data points. Right? And again, this is varying over orders of magnitude, right? So because it's a log plot, I'm doing 10 to the 8, 10 to the 9. So this is a relationship that holds over several orders of magnitude, which is going to be true of all of the neural scaling laws that we're going to look at, that they continue to be true across like many orders of magnitude of number of parameters or amount of compute or data set size. I'll pause here. Does anyone have any questions? Okay, great. Okay, finally we come to the most interesting bottleneck, the one that like actually matters practically for us in terms of training these models, which is compute. So I have as much data as I want. I can make my model arbitrarily large, but what's the, if I have a certain amount of compute to spend, how well can I do? So in order to begin answering this, we're going to consider the fact that in a transformer, each parameter, except for the vocabulary parameters, is involved in roughly one addition operation and one multiplication operation during each data point that's processed. All right? So this means that the forward compute, the compute that's used in the forward pass of the model, is 2, 1 multiplication and 1 addition, n, where n is the number of parameters, d, where d is the data set size. Does this make sense to everyone? Yeah? So this is the forward compute that I spend to process. The reason it's an approximation here is because I also have various things like nonlinearities and some other things I have to do, and these add on a small amount, but they aren't linear in the number of parameters, and they don't contribute nearly as much as this. This is where the bulk of the compute comes from. The backwards pass ends up taking roughly twice as many operations as the forward pass. And so the backwards compute is 4ND, which means that the total compute that I spend training my model is 6ND. And this presents a trade-off that I have between making my model larger and making the data set size larger. Right? If my model is larger, then with the same amount of compute, I can't process as many examples. So I can't train on as many examples. If I make my data set larger, training on more examples, then in order to train on all of those, I have to make my model smaller. Right? So there's a fundamental trade-off. If you have this amount of compute, you can either spend it on making your model larger, or you can spend it on making the data set larger, training for longer. You can't do both. You have to choose one or the other. All right? The 6 is not important. That's just a trivial prefactor. The important thing is that it's proportional to ND, so the product of number of parameters and data set size. That's the important thing. Any questions? Cool. All right, so now let's suppose I'm bottlenecked by compute. how well can I do? What can I do if I'm bottlenecked by compute? So now we're going to train models of various sizes with a very large data set, right? And then for those, we're going to plot the test loss that they achieve as a function of the compute that they use. And then we're going to plot the minimum test loss across all of those training runs as a function of the compute that it uses. And again, we get exactly the same relationship. It's exactly the same once again of the test loss is a power law relationship with the amount of compute that I have. So let's take a look at the graph. So just to help you interpret this, each of the thin blue lines represents a single training run. And what I'm doing for this training run, which has a different number of model parameters. So each of the blue lines is a different number of model parameters. And then I'm training on my data set with that many model parameters. And I'm seeing, as a function of the compute that I've expended to train it, what does the test loss look like? Again, it's a log-log plot. And you can see that these lines, the test loss as a function of compute, kind of bounce off some line. And that line that they bounce off, if I plot that line, ends up being precisely this equation here, because it's the best that I can do for a given amount of compute. Any questions? Yeah?
Is there like a reason why you should expect these logarithmic relationships?
Question was, is there a reason why you should expect these? No, not as, I mean, I'm sure there is a reason, we just don't know it. These neural scaling laws to me are absolutely fascinating. I don't think anyone has a good explanation for where they come from. Some people have some explanations. I don't think they're very good. But like, yeah, I think that these are super interesting. And if you have like a heavy physics background in like statistical mechanics or something, and you want a Nobel Prize, then like you should go and find out why these scaling laws happen. They're very interesting, but I don't think we have a good explanation yet at all. Okay. So now we're going to move on to another paper, which is training compute optimal large language models. This was several years after, this is 2022, so several years after the initial neural scaling laws paper. Essentially, the interesting thing it's doing is it's saying that, well, you can use these neural scaling laws to work out how you should expend your compute, right? So given that you have a certain amount of compute budget, you can use neural scaling laws to work out what you should spend that compute budget on, whether you should expend it on making the data set larger or making the model larger. So for a given compute budget, you have to trade off between these two things, right? You have to choose what you're going to invest your compute in. And neural scaling laws can be used practically to decide how to allocate compute. And they are used practically by large AI companies. And a large AI company wants to make a new model that's they're willing to spend this much money. This is the budget they have for that model. The budget directly translates into compute, and the compute, you can then work out how to allocate that compute using a neural scaling law. Okay, so what we're going to do is, this is step one of the methodology, is I'm going to fix a compute budget. I'm going to train models of varying parameter counts on that on however much data is necessary to reach that compute budget, right? And that gets me this curve here. This is logarithmic in x, linear in y. It gives you the training loss as a function of the number of parameters you're using in your model. And you get these curves here. These curves are called isoflop curves, right? Because they are curves defined by using the same amount of compute, so the same number of flops, and each one of the color is indicating how much compute I used, so how much compute I expended on that curve. And we can see that for all of these, they have this this kind of minimum somewhere, and that's the best you can do. That's the optimal allocation of that compute is the minimum point along this curve. All right. So we fix the compute budget, train a bunch of models. This gives me these isoflop curves. Next we're going to do is, now that we have all these data points of how much compute did I use and what loss did I end up at and what was my parameter count and what was my data set size, and now I'm going to fit this, this neural scaling law to that data, right? So before we considered bottlenecks where one of them we could One of the quantities that would be a bottleneck can just be go off to infinity, so we have infinite parameter count or infinite dataset size. Here we have finite of both, and we're going to fit this relationship here to those curves that we've got. And to break this down for you, this is the loss, and it's the sum of an irreducible loss, which is basically saying that even if you were doing text modeling perfectly, even if you knew exactly or you were doing it as well as is possible to do, you would still not do infinitely well in the loss. There would be some loss that you couldn't get rid of. And that loss that you can't get rid of comes from the entropy of the text itself. The fact that if you have multiple documents of text, then given some initial string, there will be multiple documents that continue that string in different ways. And this gives you some intrinsic randomness to the text that's impossible to model away. And this is hypothesized to be what L0 is. We don't actually know. It might be something else, but it is hypothesized that L0, the constant you end up here, ends up with is equal to this intrinsic entropy of the text. Next is the loss that comes from using only finite data. So the fact that I'm bottlenecked by data, I have this term here, which is just the term that we encountered before. And then finally, a portion of the loss that comes from having a finite model size, so the fact that I'm also bottlenecked on model size, right? So I'm going to fit this to the data set of those isoflock curves that I formed in step one. Yep, question?
When you mention compute, there are things like sort of changing the learning rate, changing the optimizer that affect that. Is that just, for the purposes of this exercise, you just kind of following like constant, allowing any optimization?
Yes, so you have to hold a bunch of things constant. So you have to hold what optimizer you're using constant. If you're doing like any other fancy things, like if you're doing like weight decay, you have to hold that constant too. An interesting thing about training compute optimal language models is that they arrive at different scaling laws because when they get their isoflock curves in step one, they make sure to use the same, for each different training run, the same annealing schedule for the learning rate. Whereas the previous paper doesn't do this until they arrive at different scaling laws. So yes, you have to hold all those details constant to do it properly. Yeah. And practically, you hold them constant at what you intend to use eventually, right? So whatever you're going to do in the final training run, once you've arrived at your scaling law and you know how to scale things, that's what you hold constant. Yeah. Okay. Great. So what's step three? Well, step three is once you have this expression, once you fit the data, so you've got your values of L0, DC, NC, alpha D, and alpha N. You've got all them. Then you can optimize it analytically using a fixed compute budget, right? So we know that the product of N and D gives you the compute, right? So the compute is 6 ND. So if I have this much compute, it means that I have to optimize my loss as a function of N and D subject to this constraint in N and D, right? And it's like a very straightforward maths exercise to do this. And if you do go through the derivation, you arrive at this relationship here. So I'm leaving out constants that arise from NC and DC, but the point is this tells you how to scale your model, right? So this is telling you, given an increase in the amount of compute I have, so an increase in the amount of C, how should N and D increase as well, right? And so once you have values of alpha D and alpha N, you can work out what these scaling relationships are, and the prefactors that come out front just come from DC and NC as well. So you can also work out them, but I'm dropping them off because they're not very interesting. Right? Okay, and once you have that relationship, it tells you how to optimally allocate compute as you scale the model. And it turns out that in this paper, the numbers they arrive at for alpha N and alpha D give you that you should in fact scale these with each other at exactly the same rate. Or these numbers are near enough to 0.5, I'm just writing 0.5 here. So this tells you that if you have 100 times as much compute, you should increase the parameter count by 10 and increase the dataset size by 10, right? Makes sense? If you have 4 times as much compute, you should double both, right? So you should scale both of them proportionally to one another and both of them proportionally to the square root of the compute. Any questions? Great, okay. So I just want to show this image. I think this image is like extremely impressive. This is taken from the GPT-4 technical report, and what they're doing is they are basically showing that scaling laws work out of the range that we're currently seeing them. So they have trained a series of very small models, and from that arrived at a scaling law of the loss as a function of the amount of compute that you have. This is normalized compute. So the 100 mu here means 100 millionths of the compute that's going to be used eventually. So what's interesting about this is that all of these points here, getting this data is a drop in the ocean compared to the amount of compute you will eventually use to train GPT-4, right? Because all of these points, to derive them, the amount of compute you need to burn is like on the order of millionths of the amount of compute that you're going to arrive at eventually. And so you can get all these points very easily, right? It doesn't cost you much at all relative to the cost of the eventual training run. And you can say with very high degree of precision and certainty what the compute you're going to end up at is in the end. And that's precisely what you get. They extrapolate the line out over like several more orders of magnitude, and they hit the point that they eventually get with GPT-4 almost bang on, right? Yeah, any questions about this? Yeah. So this is a picture showing the practical import of these neural scaling laws. Yeah.
What actually is the y-axis? Bits per word.
Bits per word is just like another measure for loss, right? Yeah. So it's again just like another way of measuring the loss, or another way of framing what the loss is.
Where GPT-4 here is not actually GPT-4, it's like the non-fine-tuned base text interpolator.
Yes, so the GPT-4 here is the unsupervised learning version, so the one that hasn't been fine-tuned at all yet. Yeah, so the base model. Yeah. Great. Okay, on to the final part of the today's lecture, which is that I'm going to argue that as you turn up the amount of compute that you're expending, as you burn more compute training these models, this buys you something. It buys you more latent capabilities within the models get smarter. So this is really a return back to what we covered in lecture 1. I want to start with this image, which I think is like really historically interesting. So this is from the 2020 State of AI report, and it shows these are all language models. It shows all of these language models by parameter count. And the interesting thing is, GPT-3 is 10 times larger than any other model that's been trained, right? And something has to like make you do this, right? You don't just like wake up one day and decide, I'm going to train a model that's 10 times as large as a model anyone else has trained, and because compute scales as the square of parameter count, that costs you 100 times as much as anyone has ever burnt on a language model, and you've decided to do it. So like, why? Why did OpenAI decide to burn this much compute training a language model this large? What motivated that? In 2019, Richard Sutton, who is one of the founding fathers of reinforcement learning as a field, writes this essay. It's not really an essay because it's extremely short, called The Bitter Lesson. Thoroughly recommend a read. It's like one A4 page. You can read it very quickly. And in it, he articulates a retrospective of the field of AI over the last 70 years, which he has been in for like nearly that long. And he says that the history of AI over the last 70 years has been repeatedly discovering something that he calls the bitter lesson. And the bitter lesson is that the most effective methods in the long run are those that can very effectively leverage large amounts of compute. So he gives two concrete examples that I think are the most important, which are search and learning. That learning as a methodology allows you to very effectively leverage more and more compute, which is exactly what we see with the neural scaling laws. The neural scaling laws tell you that if someone gives you 100 times as much compute, you can get a lower loss. You will do better, right? And so you can leverage that compute. Whereas there are many methods where if someone gives you 100 times as much compute, you can't actually do that much with it. It's not actually that helpful at that point. But learning can absorb compute and leverage it very effectively, which is why we entered this deep learning era, and why when we did, the amount of compute that we invest in these models per year increased at a much higher rate than before we entered that era, before we knew how to leverage that new compute that we got. And the reason it's called the bitter lesson is because these methods that very effectively leverage large amounts of compute are beating out over human-centric approaches. So he gives an example of chess with the success of Deep Blue beating Garry Kasparov. The Deep Blue algorithm leveraged large amounts of compute to just do like massive quantities of search through possible space that of what moves could be taken. And this beat out over many other AI practitioners who are trying to leverage human knowledge of the chess domain to like, we have centuries of people thinking about chess, and the idea was, we just need to leverage all this chess knowledge and build it into the machine. And that didn't work. It was beaten by a method that learned that was able to leverage massive amounts of compute to just do really deep search. And in the same sense, what large language models represent, what GPT-3 represents, is a leveraging of a large amount of compute in the domain of general intelligence, finding that there is a way that you can pour in compute to get models that are like always smarter the more compute you throw in. And that's what the neural scaling laws tell you. In 2020, Gwern, who's an essayist, I guess, publishes a post called the scaling hypothesis, where he articulates the kind of mindset that he thinks that OpenAI had when they were training these models. And he puts forward this idea called the strong scaling hypothesis. The strong scaling hypothesis is that once we find a scalable architecture, we can simply train ever larger neural networks, and ever more sophisticated behavior will emerge naturally as the easiest way to optimize for all the tasks and data. This is exactly what I was talking about in the first lecture, right? That if you have a very large data set, with many, many tasks embedded within that data set, then if you just train a model that's large, if you just keep pouring compute in, you will have a way to leverage that compute to learn all of these tasks simultaneously, and that learning all of these tasks simultaneously causes you to learn something that looks like general intelligence. So let's review historically how this played out. In 2019, OpenAI publishes a paper which is language models are unsupervised multitask learners. This is the GPT-2 paper, and this is where they get a taste of scaling, right? So they train this family of models, the GPT-2 family, on next token prediction, and they test it on various NLP benchmarks. NLP stands for natural language processing. And the important thing, the interesting thing, is that they test it out of the box, right? So many previous people had used unsupervised learning, generative pre-training, to basically kickstart the model. So you kickstart the model by making it do generative pre-training, and then you train it on some particular task that you care about, some particular element of natural language processing that you want to get good at. But what they do is they just train this model that's quite large at the time by that standards, and they find that it does well at NLP benchmarks out of the box with no further fine-tuning, no further refinements, right? They just throw it at tasks and find that it can already do the tasks pretty well. It has not been trained to do the tasks. No one has made it. It has just been trained on a massive suite of data and internalized basic cognitive mechanisms for completing a lot of the NLP benchmarks that were prevalent at the time. So here's some examples of different benchmarks. And here we're sweeping over, again, logarithmically, we're sweeping over the number of parameters that we've got in the LM model, which we know sort of corresponds to the amount of compute thrown at the LM model. And as you can see, on tasks like reading comprehension, translation, summarization, and question answering, the score of the model, the ability of the model to do well, goes up as we begin throwing more compute at the model, right? And this is what they take as a signal that, if we just throw more compute at the model, maybe we can do much better, right? Maybe if we go up several orders of magnitude, we'll be able to do a much more impressive job than if we're just sweeping over these comparatively quite small models, right? So the largest model here is, again, 1.5 billion. One particularly interesting one of this is that the model does not terrible at translation, despite being trained on predominantly an English language corpus. right? They haven't trained it on French text, but there's some French text in an English language corpus, and it turns out that it's pretty good at translation out of the box, having just trained on an English corpus with no fine-tuning on translation tasks. Questions?
This might be like a very long way out of your expertise. I'm kind of curious what the scaling law would be in terms of the size of the subcorpus that contains foreign language.
Yeah, I'm not sure about this. Yeah.
Because I can think of like several different possible hypotheses.
Yeah. I don't think anyone has scaling laws for like subtasks within the larger data set that you're training on. Or maybe it's just the like logical law that you would get, but like I'm not sure about this yet. Okay. Great. So then in 2020, they sort of run with this idea. So they publish another piece, which is language models of few-shot learners, and basically training GPT-2 demonstrated that if you just train models that are bigger, then they get better at lots of downstream tasks without you needing to fine-tune them or scaffold them or modify them at all. You can just do next token pre-training, and you don't need to do anything beyond that, and you automatically get good performance at lots of downstream tasks. So what if we do this, but bigger, right? What if we just do this, but 2 orders of magnitude larger than we did before, right? What if we train something that's got 175 billion parameters rather than 1.5 billion? That's 10 times bigger than the frontier model at the time. What do you get, right? So GPT-3, which is the largest ones that they show, has abilities not present in GPT-2. In particular, GPT-3 demonstrates very powerful in-context learning, right? And in-context learning is the ability to learn a new task from examples of that task provided in the prompt, right? So you provide a textual description of the task you want it to complete, so natural language description of this is what I want to happen, and then you provide some examples of that task being done, and then you give it a new example and you see how well it does. This is what we call in-context learning. And basically they make this argument that, well, if you're training on a large amount of data sets, then you can see as, tacitly within that data set that you're training on, there will be many of these in-context learning tasks embedded. For example, if somewhere in the data set there is a French to English dictionary or something like this, a French to English translation, then as you train on that, you are training to be able to do in-context learning on that kind of task. But it's not just that you're learning to do that task, it's that you're learning a general method for learning from information that's present in your context, right? And that's what we call in-context learning. And they give other examples of arithmetic and reversing, unscrambling words. So here are the results. So again, this is not like a fine-tuned model, this is the base model. The model that's only been trained with unsupervised learning, no scaffolding, no fine-tuning. And we're looking at the ability of that model as we sweep across the number of parameters and as we increase the number of examples that it gets to look at. And we can see already that on some of these, the zero-shot version, the version that doesn't see any examples, already does very well, right? So this is the SAT analogies. So it's part of the SAT test that you take in high schools. We see that as we make the model bigger, as we sweep across the number of parameters, it reliably gets better at completing these kinds of analogies. And moreover, for the larger models, having examples, so being few shots, so seeing 20 examples of the kind of task that you're supposed to complete, increases the model behavior by quite a lot when it gets very large. This is a conversational question answering dataset. It's essentially just reading comprehension. And they show that the accuracy of these models on reading comprehension goes up massively as you increase the model size. And look, the human baseline is something like 87%, something around that. And you're already at 80-something, 85 something with it's just below 90%. So it's just below 90, and you're already at 85 with the few-shot model, right? And this is a crazy thing to discover. It's absolutely crazy at the time that you just train a model that's really, really large, and out of the box, with no further work at all, it's already getting like comparable scores on reading comprehension to actual humans. This is nuts, right? This is a physical question answering data set. So it's common sense questions about the physical world. And we can see that GPT-3, again, with no scaffolding, is able to beat the state of the art at the time, which is a fine-tuned model that's been like heavily trained to do this kind of task, right? Whereas GPT-3 is able to do it better than state of the art, just generally. And next is trivia. Again, it beats fine-tuned state of the art just straight out of the box when you give it these a few shot learning prompts to go off. Yeah.
I may be forgetting, but I'm not sure you've defined what fine-tuning is in this lecture series.
Yeah, so fine-tuning here, we're going to cover more of this next lecture, but this basically just means, for our purposes, it's going to mean just optimizing for that particular task that you're looking at, right? So here we're comparing GPT-3's performance out of the box to various methods that are optimized for particular tasks. So and we can see that GPT-3 is already a generalist. It's already able to do better at physical question answering and question answering about trivia, and almost is up to the level of being able to do state-of-the-art reading comprehension just straight out of the box as compared to specialist models that are trained specifically for those particular benchmarks. So what does this tell you in the end? So training on next token prediction can be seen as training on a battery of diverse tasks that exists within that textual data set. And that when you learn in that textual data set, you're not just learning to complete the individual tasks that you see in the data set, you're also learning how to learn to solve new tasks from examples of those tasks. And this is called meta-learning, or learning how to learn. And so this is an ability that emerges in a model at scale, that when you make the model sufficiently large, when you pour enough compute into it, the model doesn't just learn to do specific things, it also learns a more general faculty of being able to learn from examples how to do a new task that you give it, which is meta-learning. And LLMs gain many latent capabilities in pre-training. How does this demonstrate that? Well, we see that just as a general rule, giving examples gets you a better score than if you zero-shot it. So if you have no examples, you're just given a textual description of this is what you're meant to do. Giving examples generally increases the performance. What does this tell you? Well, this tells you that if you do the naive thing and you just ask the language model, to complete this task, it will give you an answer, but that doesn't necessarily mean the model isn't capable of giving you a better answer when scaffolded. So if you're able to bring those latent capabilities out of the model. And this is precisely what we're going to cover in the next part of the course. So in the next 4 lectures that follow this, we're going to cover in greater detail how you bring out the abilities of a model that are hiding within that. And finally, that there are various capabilities that emerge at scale that aren't present in smaller models. You have a smaller model, but when you train a larger one, you get a difference in kind, not just a difference in performance. So as further evidence of this, there's this paper, Emergent Abilities of Large Language Models, and it plots a number of different data sets, so a number of different tasks, and it looks at the performance of models on those tasks as you vary the size of the model. And you can see that there are a lot of capabilities for which the model is basically unable to do it, so not very capable at all, until you reach a certain threshold, and then the model begins to display that capability, right? So a lot of these, they're basically flat at the start, and then they pick up after you reach a certain threshold. And this is more evidence to the fact that as you make these models larger, sometimes they pick up new things that they could do that they couldn't do before, where difference in scale, difference in the amount of compute you pour at them, amounts to a difference in the qualitative abilities of the model to perform various tasks. Here's another example of this. This is again from the GPT-4 technical report, and this is comparing GPT-4's performance. This is after various post-training modifications. So fine-tuning, which we're going to talk about in next lecture, but this is GPT-4's performance as compared to GPT 3.5's performance. So GPT 3.5 is a fine-tuned and post-trained version of GPT-3, and we can see that on some of these different tests that we give the model, its increase in performance is pretty marginal. It's like small incremental increases. But there are also some tests where going from 3.5 to 4, so pushing up a generation, moving, increasing the number of model the parameter count of the model gives you just massively better performance. Just like you go from basically being completely incompetent at the task to being able to do it very well, or in some cases unable to do it at all, to doing it like kind of okay, right? So this one here is AP Calculus, and as we see, GPT 3.5 is basically completely incapable of this, but 4 can do it very well, right? Or sorry, can do it like at above a trivial level, right? So what are the key takeaways of the lecture? What I like to leave you with? So the first is that this idea of the strong scaling hypothesis, the idea that you don't necessarily need particularly clever tricks to get intelligent systems, you just need ways that you can leverage very large amounts of compute. So ways that you can, or training regimes or methods where if you throw in 100 times as much compute, you will get better performance. So effective ways to leverage compute. And as we've seen, we have like strong historical reason to believe that as we continue going, the amount of compute that will become available for training these models, so the amount of compute that is available to leverage, will increase in this geometric fashion of like 5 times as much compute per year. The second is that as you leverage more and more compute, as you make the models larger or you find like better ways to leverage this compute, sometimes you get new abilities that aren't present in smaller models. If a smaller model can't do something, it is not a sign that this method in and of itself is a dead end, and that because it may be the case that if you make the model 10 times as large or 100 times as large, it suddenly is able to do something that it wasn't able to do before. And that historically speaking, this trend will probably continue, that more compute will be used to train these models, we will throw larger and larger amounts of compute at them, and that those models that we get will very reliably have a lower loss. And with that lower loss becomes a better understanding of the processes behind the text and a better understanding of what's happening and more latent capabilities. And progress is going to continue in the next decade as we find more effective ways to leverage large amounts of compute. Thank you all very much.